Over the course of history, approximately 108 billion people have lived on our planet. Yet only one person realized that our universe is woven from the fabric of space-time. And this realization is the key to truly understanding Einstein's genius. Imagine if you were a fish. Could you, through intuition alone, recognize that you were submerged in water? Probably not. Fish cannot perceive the water they live in. It is simply their natural environment. Humanity up until 1915 was in exactly the same position. If we truly want to grasp general relativity, we need to align our thinking with Einstein's perspective. Consider this. Just as a fish exists within water, we exist within the fabric of space-time. This is our ocean. Yet we do not notice it, because we are part of it. In 1915, Einstein introduced his general theory of relativity, a breakthrough that redefined our understanding of gravity. It remains one of the cornerstones of modern physics, exploring the intricate relationship between space, time, and matter, and answering some of the deepest questions about our universe. But let's be honest. A definition like this makes perfect sense to people whose daily work revolves around physics and mathematics. But for science enthusiasts like us, it often leads to that familiar feeling. Okay, I get it. I think. The truth is, truly grasping general relativity, the moment where you can confidently say, yes, I understand this, often requires a simpler and more visual approach. So, how do we reach that level of understanding? This is where small but significant bugs come into play. Einstein's journey toward this revolutionary insight actually began with one of these bugs. And we are going to follow the same path. The orbit of Mercury around the Sun showed a slight deviation when calculated using Newton's laws. At first glance, this might seem like a minor detail, but for scientists, it was a major issue, a bug in the system. Einstein couldn't just accept this. If Newton's so-called universal laws failed to accurately predict Mercury's orbit, then perhaps these laws weren't truly universal after all. But questioning Newton at the time was a risky move. It meant facing rejection from the entire scientific community. Still, Einstein took that risk because in science, courage is more valuable than anything. He had an idea. What if the Sun wasn't just affecting Mercury's orbit through gravity alone? What if it was bending the very fabric of space-time itself? What if the massive presence of the Sun, our primary source of light and energy, was actually distorting the invisible structure of reality itself, altering the path that Mercury followed? In 1915, to propose that the universe could be stretched and bent required an unimaginable level of creativity and vision. What does it mean for space-time to be curved? To truly grasp this concept, one that lies at the very heart of general relativity, let's start with a simple analogy. Imagine you board the Amtrak Acela Express train, traveling from New York to Philadelphia. The distance between these two cities is about 100 kilometers, and if the train moves at 100 kilometers h, it will complete the journey in exactly 1 hour. But now let's change the scenario. Imagine someone like Elon Musk, a tech entrepreneur with a vision for disruptive projects, decides to build a massive roller coaster along this route. Even though the train maintains the same speed, the new track, filled with extreme ups and downs, extends the total distance to 120 kilometers as a result. Even though the train is still traveling at 100 kilometers h, it will now take 1 hour and 12 minutes to complete the journey. Einstein's theory explained a similar situation, but on a cosmic scale. The Sun bends space-time, and this curvature causes the very same kind of distortion in Mercury's orbit, leading to the deviation that Newton's equations couldn't fully explain. At this moment, Einstein experienced a profound realization. If we accept that space-time itself can be curved, then general relativity offers a radically different explanation of what Newton once called gravity. Newton believed that gravity was a force pulling objects toward one another. But Einstein argued something completely different. Gravity is not a force, but rather the curvature of space-time itself. Although explaining this concept in 2 dimensions may help visualize it, true understanding requires thinking in 4 dimensions. The fabric of space-time isn't just like a flat rubber sheet. It extends across 4 dimensions, 3 spatial dimensions plus time. Now, imagine looking at the space-time fabric in its full 4-dimensional structure, as you see on the screen. If a massive object or a high-energy source is present, it bends the fabric of space-time in all directions, not just in 2 dimensions. As you move farther from the massive object, the curvature weakens. But as you approach the object, the bending intensifies, distorting the paths of anything traveling through this space, including planets, light, and even time itself. The essence of it all is this: a massive object, like the Sun, warps the very fabric of space-time that Earth exists within. This warping curves the path that Earth follows. The distortion created by our star keeps Earth locked in its orbit. So rather than a gravitational force pulling Earth in, what we actually see is a natural consequence of the curved space-time that the Sun creates. Now is the perfect time to ask a question that has puzzled many. If space-time is so curved, why doesn't Earth fall straight into the Sun? Let's start with an everyday analogy. Imagine you drop a ball into a pit. Naturally, gravity will pull it downward, and the ball will accelerate into the hole until it reaches the bottom. Simple, right? But if we apply this same logic to planetary motion, why doesn't Earth just plunge into the Sun's gravitational well? The answer: it all comes down to speed. Earth moves at an astonishing 30 kilometers per second around the Sun. This speed is so great that it prevents Earth from falling directly into the Sun. Even though Earth is continuously being pulled inward by the Sun's gravitational influence, its immense velocity allows it to keep orbiting rather than crashing inward. Imagine a rock tied to a string. If you swing it in a circle and suddenly let go of the string, the rock won't fly toward the center. It will shoot off in a straight line. If Earth ever lost its speed, it would spiral straight into the Sun. This brings us to another frequently asked question. If Earth is moving this fast, why don't we feel it? The answer is simple. Our motion is constant. You don't feel speed itself. You feel changes in speed, acceleration, or deceleration. Think about when you're in a car. If you're moving at a steady speed on a smooth highway, you barely notice it. But when the car speeds up, slows down, or turns, you feel the forces acting on your body. Earth's motion around the Sun is incredibly smooth and consistent, which is why we never notice it. Imagine you are in a car, but this time you are completely alone. You close your eyes and cover your ears, completely isolating yourself from the outside world. If the car is moving at a constant speed, you wouldn't feel the motion at all. But the moment the car brakes or accelerates, you would immediately notice it. This is exactly why we don't feel Earth's movement around the Sun. The Earth's speed is constant, and because there is no sudden acceleration or deceleration, we remain unaware of our journey through space. Now, coming back to our topic, the precise calculation of Mercury's orbital shift using general relativity equations was the first direct confirmation that space-time could be curved. This was a groundbreaking moment for physics. But if this isn't a clear enough example for you, let's look at it from a different angle. One of the most compelling pieces of evidence for space-time curvature comes from gravitational waves, something we frequently mention in our videos. How do we know they exist? In 2015, the LIGO detectors succeeded in measuring gravitational waves caused by the collision of two black holes. These ripples in space-time prove that space itself can vibrate like the surface of an ocean. This discovery did not just confirm that the fabric of the universe can bend, but also showed us that it can ripple and oscillate like waves on water. Einstein was right. In summary, this theory explains that gravity is not some mystical attraction force pulling objects together. Instead, it is the natural result of space-time curvature, just as Einstein had predicted. One of the most fascinating aspects of general relativity, one that has inspired countless works of science fiction, is time dilation, a direct consequence of the curvature of space-time. In regions where massive objects or intense energy fields exist, time flows more slowly relative to an outside observer. This phenomenon was the inspiration behind one of the most memorable scenes in the movie Interstellar. When Cooper landed on a planet orbiting the black hole Gargantua, the immense gravitational pull caused time to slow down for him. Meanwhile, back on Earth, his daughter Murphy experienced time at a normal rate. As a result, when Cooper returned, his daughter had grown into an adult, while he had barely aged at all. In general relativity, space and time are not separate entities. In addition to the three dimensions of space that we experience, there is also the dimension of time. Together, they form the four-dimensional concept of space-time, which is always measure relative to a specific frame of reference. When near a massive object or moving at high speeds, time in one reference frame appears to slow down relative to another. And this is exactly where general relativity gets its name. Everything is relative and depends on the observer's frame of reference. The term relativity in the theory expresses this fundamental idea. Space and time are intertwined into a single entity, space-time. This warping effect, caused by massive objects, results in time flowing more slowly in their vicinity, making it not only a scientific reality, but also an idea that fuels the imagination. The time dilation stories we see in movies are not just science fiction, they are a direct reflection of Einstein's powerful theory. Time is not just something we measure with clocks. It is an intrinsic part of the fabric of the universe, a dimension that is not fixed but instead influenced by mass and energy. In regions with strong gravitational fields or near massive objects, time flows more slowly. We don't notice this effect in our daily lives, but with precise measurements, it can be observed. For example, a clock at the top of Mount Everest ticks slightly faster than a clock at sea level. Why? Because at Everest's peak, the gravitational field is weaker, meaning that space-time is less curved. However, this difference is so minuscule that ordinary clocks cannot detect it. It's only measurable with atomic clocks, where the discrepancy is just a few billionths of a second. If you were to ask, what is the most fascinating prediction of general relativity? My answer would undoubtedly be black holes. Trying to explain general relativity without black holes would be incomplete because they are the most extreme manifestation of space-time curvature. However, black holes do not just curve space, they also warp time itself. For an observer looking from the outside, time appears to freeze at the event horizon of a black hole. This is one of the most striking indications that space-time is not just a passive stage for the universe, but a dynamic entity that can be stretched and twisted in extreme ways. The warping of space-time around a black hole becomes so extreme that no force, no velocity, not even the speed of light, can escape its gravitational grip. Think of it like this. A black hole creates such an incredibly steep slope in space-time that even light itself cannot climb out. The moment light enters this gravitational abyss, it is trapped, spiraling into the singularity. But how does space-time become so steep in the first place? The answer lies in the incredible density of mass compressed into an impossibly small space. Let's illustrate it with a simple analogy. Imagine pressing down on a balloon with your hand to create a small indentation. Now, try pressing down with just one finger instead, which creates a deeper, steeper indentation. Your finger, even though the force is the same, focusing it on a small point creates a much sharper curve. This is exactly what happens in black holes. An enormous amount of mass collapses into an incredibly tiny point, creating a warping of spacetime so extreme that it forms a cosmic trap. According to current data, a star must have at least 8 times the mass of the Sun to form a black hole. If the core of such a massive star collapses under its own gravity at the end of its life cycle, it becomes so dense that it bends space-time into an inescapable slope where not even light can find its way out. Today, we may have pushed the boundaries of science a little further in the name of visualization. But if we've managed to clear up some of your questions about general relativity, then we've done our job. See you in the next video.